So if you may listen without trying to write everything and trying to understand, or if you can do both, that's fine, but I'll post all this today. So that person is standing on a scale there, and it's going up or down? That's what you have to find, right? Because the answers say up, down, and all that. So what's the formula for this? Reaction on the floor of the lift? It should be m times g plus or minus a, depending on the direction in which it's going, okay, plus or minus a. Can you tell me when the scale would read a bigger number? Is it when it's going up or down? Up. So you know if it's going up, it's g plus a. If it's going down, it's g minus a. That's how you remember that. So plus when it's going up and minus when it's going down. And therefore, according to this question, 400 is what it reads. The mass is 60, and then g minus a. Okay. And if you solve that, you would get 3.13 meter per second squared. So that means it's going down, and the acceleration is 3.13 meter per second. All right. When you read the second one, you understand that it's there is no banking for this road, right? There is no banking. If at all it has to stay on that curve, it has got to do that using friction. So there's only friction. If there's only friction, then you know the centripetal force has to be provided by friction. So there's no banking, there's only friction, and you know that the centripetal force is given by mv squared by r. And friction is mu mg. On a flat surface, the normal reaction is equal to mg, isn't it? And friction is mu times Fn, so I've put mu mg, okay, because Fn is equal to mg. So that's friction. The masses get cancelled, and then you take the square root of that, you would get 37 meter per second. Anybody got that? Okay. Well, in this question, just understand that it is already in a circular parking orbit. That means it's in a stationary orbit, right? And it has to be moved just a little bit. That's what you mean by Hofmann transfer. So you have to fire a small rocket, so it has a force acting on it, and the speed is increased. You see, when the speed is increased, wouldn't the radius of the orbit change? Yes, it would. That's the intention. So we want to shift it a little bit, and so you're firing a rocket, and the speed has increased to 8,300 meter per second now. And the question is, how far from the center of the Earth will the satellite be when it reaches its apogee? Means if it's an elliptical orbit, it's at different distances from the Earth. Apogee is the maximum distance from the Earth. You know, for an ellipse, the distance keeps changing. We've talked about that. So that is the maximum distance from the Earth. You're given the mass, you are given the universal gravitational constant. Like we saw today, the kinetic energy must be equal to the work required. Let me stop it right there. Do you remember that formula, Gmm by R, that we derived today? Didn't we get that for the work? Isn't that what we got for the work? So initially, the radius of orbit is R1, and then it is R2. Therefore, you have got to take the difference to get the work. That's what I've done there. If you do that, don't you get the work? And then what I did is, this is common, so I've taken it out. And therefore, you have 1 by R1 minus 1 by R2. So that's the simple thing. If you're trying to make it escape, then you know R2 is infinity and R1 is the radius of the Earth, because you start from the radius of the Earth and get to infinity. But here, this is a general formula which you have to remember. Okay, so the masses get cancelled. Now substitute what's given. The velocity is given, 8,300. And then that's the number that you get on the left-hand side. Rearrange it. I've taken g times m to the denominator. We're looking for R2, so I'm trying to make that the subject. There is some calculation involved. Finally, I substitute the constant and the mass of the Earth. Minus 1 by the radius of the parking orbit. You have to be careful when you calculate that. So I've calculated those separately. Get the difference. And now I've got to take the reciprocal of that, isn't it? To get the answer. That is the answer. Well, I'm trying to explain that that is supposed to be 1/2 mass 8300 squared minus 7900 squared. Where did I get that 7900 squared from? Any idea? Come on. Does anyone remember that number? 7.9 kilometers per second? If a satellite is orbiting close to the surface of the Earth, that is the speed. Okay? Hopefully. So the initial potential energy, 1/2 kx squared. Okay. A and B are the 2 points. You stretched it down to A, then let it go. You're asked to find the speed when it reaches B. So 1/2, that is 1 centimeter. So 1/2 kx squared at A, that's too slow, is 1/2 kx squared at B plus 1/2 mv squared at B. Cancels that. I cancel the halves. Now it's all math. K is common, so I've taken it out. And now you're looking for the speed or velocity. So I've just rearranged it. K is 100. Wait, but isn't K given as 1? That's Newton per centimeter. So if it's 1 Newton per centimeter, it's going to be 100 newtons per meter. Okay, that's how I have the 100. And then you also notice that the distances have been changed into meters. That's 2 centimeter, and that's 1 centimeter in meters. Mass has to be in kilograms. So when you do all that, you get 0.173 meter per second. The idea is that if any object is being lifted, the work done is equal to the change in its gravitational potential energy, which is mgh, and power is work over time. In this case, work is mgh, so it's mgh by time. You have the quantities there, the time is given, there's nothing there in that question. It's 736 watts. By the by, that's almost 1 horsepower. Have you heard of horsepower, HP? That's 746, but this is so close. I do want to tell you something that's really useful throughout physics. I want to tell you this, that this is always the relation between force and potential energy. Always. Because you're going to have gravitational potential energy, elastic, magnetic, electrical. Wherever you have potential energy, this works. The force is always the negative gradient of potential energy with distance. That's the symbol for potential energy. That's force. Now, can we turn this into an integral? Can somebody help me to write this as an integral? This is, I've used differentiation. Can you, come on, anybody? U is equal to of f Correct? Minus. Now, do you realize that this is work? You don't. This is work. And how do you define potential energy? For example, when you lift an object from the ground, how do you get the formula mgh? It's simply the work done in lifting it, isn't it? That's the idea. Potential energy is always the total. Integration shows total. It's the total work done in doing something. Maybe lifting an object or stretching a spring, whatever it is. This is an all-important equation. It's going to be used throughout physics. Okay? Now that is what this question is based on. That's why I do. You have a graph, and look at the axis, please. What are the axes? What's on the x-axis and what's on the y-axis? It's not so clear on my diagram. What's on the x-axis? X. And on the y-axis you have u. So if you take the slope, you know you get the force, right? du by dx is nothing but the slope. In fact, the negative of the slope will give you the force. What are you asked to find? Find the force. Find the force as a function of position. So all you got to do is, okay, there I've written it slightly different, but it's the same thing. You know that for a spring, potential energy is 1/2 kx squared, don't you? Okay. So if you differentiate that, you're going to get kx, which we know is true. Hey, don't we know that F is equal to kx for a spring? Are you with me? So from one you can go to the other. If you integrate kx, you're definitely going to get 1/2 kx squared. Isn't that true? Yeah. If you integrate kx, you're going to get 1/2 kx squared. So think about it. Now look at the question, then you'll understand why I got that. There are 3 parts for the graph, isn't it? All I'm doing is just taking the slope of all the 3 regions. That's all I've done. Now everybody knows that in this part the slope is, what's the slope here? 0. Yeah, that's why I've got that. And then x between -5 and -2 is this part. See that? I found the slope of that part, I got it as 2. Then I found the slope of this part, just, of course, having a smaller slope, I got it as 1. That's it. So the simple idea is F is minus du by dx, which will help you. Why? Somebody tell me. That's a good question. Why isn't it not negative? You know, the formula itself has a negative. Did you notice that?
Negative slope is
Actually, that's a negative slope. Everybody understands that. But 2 negatives make a? Correct. That's why.
negative slope is equal to the force, right?
Yes. Negative slope is equal to the force. So since that's already negative, became positive. You got time to read that. That's position A, and it's moving with a speed of 20 meters per second at that point. And then the vertical height is 200 meters there. And you are asked to find what's the total energy of the roller coaster at point A. It only has, I got you, it has both. Doesn't it have both? Okay, so you'll have to find mgh and 1/2 mv squared, add them up. Okay, so at A, it has both. All quantities given, nothing in this question. It's easy. Okay, and then B says, what is the total energy at point B? Come on now. Total energy has got to be the same. So energy is conserved, so it'll be the same number. total energy at B is the same thing. And then C says, what is the speed at point B? At point B, what is the potential energy? It actually says that here, you know. See that? Because isn't that where we measure the height from? So at that point, the potential energy is 0. Therefore, it only has kinetic energy. So you set the total energy equal to 1/2 mass times velocity squared. And then calculate for the velocity. Because it's entirely kinetic. And in the D part, says, what is the speed at point C? Same thing again. At point C, it has both, doesn't it? But they should still add up to the same number. So the idea here is that the total energy is always constant. In any case, whether it's gravitational potential energy or elastic, the total should be the same. So the final answer is 34.4 meters per second. Would you have got that on the exam? There is no friction. The object, the mass is given, 0.5 kilograms. It's actually compressing a spring by a distance of 12 centimeters. So the spring is compressed. You have to visualize that. And then the object is released. The object leaves the spring at a speed of 20 centimeters per second. So when the spring is compressed, what type of energy does it have? Potential. That's 1/2 kx squared, isn't it? And when you release that, all of that becomes kinetic. That's all. So you got to put those two equal to each other. The initial potential energy of the spring, 1/2 kx squared, is equal to the kinetic energy of the object. That's all. And then rearrange, calculate K. (1.39 Newton per meter). A cyclist does work at the rate of 500 watts while riding. So that's power, of course, isn't it? How much force does her foot push with when she's traveling at 8 meters per second? Does anybody know the formula, connection between power and velocity? We've used it. That's it. Power is force times velocity. Straightforward, because power is work over time. Work is force times displacement, and then you can divide displacement by time. That gives you velocity. So that's a new formula there. Power is force multiplied by velocity. You plug it into that, 63 newtons is the force that she applies. How do you do this question? What's the change in the kinetic energy? I'm trying to remind you about the work energy theorem. Do you remember that? Work done is equal to change in kinetic energy. Got to write that down. Work done is equal to change in kinetic energy all the time. So just find the change in kinetic energy. Or find the work done. In fact, in this case, find the work done. You have. So that's change in kinetic energy is equal to work done. Work is force times displacement. So easy, isn't it? When I picked this, I'm trying to remind you about the equations. You see, not just the math. Change in kinetic energy is equal to work done. Keep that in mind all the time. In this case, the man is lifting a bucket of concrete from the ground up to the top of a 30-meter tall building. So the man is giving it potential energy. The bucket is initially at rest, but it's traveling at 4 meters per second. When it reaches the top, how much work was done by the man in lifting the bucket? Work done is change in potential energy, in this case, plus the change in kinetic energy. Didn't both change? Come on. Didn't both change? Nobody's here. Because at the ground, the potential energy is zero. So when you lift it, the potential energy changes. It's also speeding up. So in this case, work done is change in potential plus change in kinetic. And change in potential is mg, change in height, plus change in kinetic is 1/2 times mass, change in velocity squared. All you got to do is plug in those numbers. .04 kilojoules. The question here is how much work is done. What's the general formula for work? What is the formula for work? If you say force times distance, it's wrong. If you say F dot D, it's correct. Because F dot D means FD cos theta. Isn't it? And what's the theta? Theta is the angle between force and displacement. So you'll have to make out that angle. Can somebody tell me what's the angle between force and displacement in this?
160.
So that's the important thing. Find out from the diagram that you drew. What is the angle between the force? I mean, it's the force due to the wind blowing, isn't it? And the displacement. So can you make out that angle? Here's the diagram. That's the east. That is 30 degrees north of east. That's how the airplane is flying, right that way. Okay. And that's 30 degrees. Okay. That is now 10 degrees south of west. So from the west. So that angle is 10 degrees. You know why I drew that? Does anybody understand that that is going to be 20? Surely that is 20, isn't it? Because I just extended this backwards. That's 20. Now, that's the force applied by the wind. That's 2.4 kilonewtons, which is 2,400 newtons. And I'm trying to say that this, I'm actually resolving this into two components. Isn't this going to be cos because it's the adjacent side? Come on. Yes. And that's exactly opposite to how the airplane is flying. So I took that and then I said work is multiply the two because I've already taken the cos there. I get the work as 2.7 times 10 to the 8. And of course the work done is against, that's why it's negative. Do you see the force decreasing up to 3 meters, all the way from 4 to 1, and then the force is constant. Force is constant at 1 Newton. That's what you understand from the graph. And then it says if an object is moving at 2.5 when it's just located at x is equal to 2 meter, what will its speed be when it reaches x is equal to 8 meter?
So really you usually see if it's doing it 3.
Okay? We can, yeah, get the answer. So let me explain that. I just told you that work is force times displacement. So area of the force versus displacement graph will give you that. And in this question, we are only talking about the time from 2 to 8 seconds. 2 to 8 meters, isn't it? 2 to 8. So that's 2, that's 8. So you got to find the area of this graph. And so you have a rectangle and a tiny triangle there. Tiny triangle. And so this is 0.5, that's the area of this triangle. And then plus this is 6. I don't know why I put it as 5 in the beginning. So it's 6 times 1 instead of 5 times 1. So you get 6.5. So the total work done is 6.5 joules. And we know that work done should be equal to change in kinetic energy. So I put that work is equal to change in kinetic energy, 1/2 times mass times the final velocity which we are looking for, minus the initial velocity which is given. It's given, 2.5. So that's only calculation now. When you calculate, you get 10.58 meter per second, which is not in the, oh, you have to take the square root of that. When you take the square root of that, you get 3.3 meter per second. Yeah, so that's the answer, because it's V2 squared there. Take the square root of this, you get 3.3 meter per second. You have to calculate the period and the speed. We know that the gravitational force is the centripetal force in this case. And so the centripetal force is mv squared by r. Set it equal to the gravitational force. Cancel those terms and you get the velocity. That's an important equation because it shows that the velocity is inversely proportional to the radius. In this case, it says it's just above the Earth's surface, so this will become the radius of the Earth, wouldn't it? Just above the, okay. So the radius is equal to the radius of the Earth, and substitute that. If you put in all those numbers, mass of the Earth will be given to you. The radius of the Earth will also be given. It should be in meters. You will get 7,900 meter per second, which is 7.9 kilometers per second.
Did you give us all those values?
Mass of the Earth and radius of the Earth, yes. And then time period would be the distance divided by the speed. Distance is the circumference. So you get it as 5,066 seconds. Somebody divide that by 60 and let's see how many minutes that is, because that's a good number, you know. Any satellite that's going around the Earth is going to take that much time for making one orbit. How much is that? 84? Okay.
That's actually fast.
It is. That's what every satellite does if it's close to the surface of the Earth. In 1 hour and approximately 20 minutes, it makes one orbit around the Earth. Because if we have it in seconds, we have no idea. Okay, let's go on to the next one. Since it's the same question and it's to find the period of a satellite, but it's circling Mars.
Doesn't matter, you shift it.
Yeah, you just change the mass, but it's 100 kilometers above the planet's surface. So, yeah, add that to the radius. Radius is given. Has to be in meters. Again, many people forget that. So that's the actual radius, and then use the same formula as before. And when you calculate that, you get 1.22 times 10 to the 7 meter per second. That is a lot faster than the satellite orbiting the Earth. Did you notice that? It was only 7,900 for a satellite of the Earth, but for Mars, it's that big. And the time period comes out to be 1.79 hours. Is it a bigger planet? I mean, in terms of mass, look at the mass. Compare it with the mass of the Earth. It's smaller. But the size, the radius is
Yeah, its radius is
larger.
larger.
That means it's less dense, correct? It's gas, yeah. So that's why that change in orbital velocity. All right, brings us to 16, because I want you to go out in 2 hours. I'll go straight into it because it's the same kind of question. So you're asked to find the period again, find the radius, add the height to the radius of the Earth. I forgot to put the units there. Oh, I put it. Okay. Mass of the Earth, of course. So that's the orbital velocity of the International Space Station, 7.6 kilometers per second. And you can tell everybody that you know the height, 370 kilometers above the Earth's surface. Time period, (5,514 seconds) is how much it takes to make one rotation around the Earth.
31 minutes.
How many minutes?
92 minutes.
92 minutes. Almost 1 hour, 30 minutes. Yeah. All right, that takes us to number 17. And it's all yours. Let's see that.
Show it how.
Okay.
We didn't do too many.
No. So by Kepler's third law, T squared is proportional to R cubed. Oh, I put it backwards. I'm sorry. It's T squared proportional to R cubed. Please correct that. On the screen, I put it as T cubed. Do you see that? It's T squared proportional to R cubed. So what you see now is correct. And therefore, if you take the ratio and you're asked to find the time period of moon B, so make that the subject. Do that simple math. And then take the square root. Where did I get that 4R? See, what's given is moon A has an orbital radius R and moon B has 4 times, isn't it? So 4 times, and that's the radius. And 4 cube is 64, isn't it? Cancel that. Forgot to put square root, so I did that now, and you get 160 days. Therefore, there is an acceleration, and that is called the centripetal acceleration. So all you had to do was find the centripetal acceleration. Just had to recognize that that is centripetal. See, this could have been a good question because I did not mention centripetal acceleration. Did you notice that? So if I had asked you a question like this, that would have been a good one. Not 10 points, but at least 3 points. You have to make out that it's centripetal and do that. Okay. And 19, I don't have the question for 19 on this. So please look at 19. That's a good one. Actually, we already did that, isn't it, at the beginning? If there's only friction, it's a flat curve, there is no banking, so it's only friction. Didn't we do that? I thought that was the first question or something. Second one? Yeah, so same thing. So 19, we did this. Centripetal force is equal to frictional force, and so you have this formula already. All you had to do was substitute those numbers. 42 meters per second. All right, the key part of this question would be to read the last part and says, when its tires just barely lose contact with the road when it's at the top of the hill. Yes, Kay?
Is it 34.3?
I don't remember the answer. It should be. What's your idea?
I said mv squared over r equal to mg.
Finish. That's it. That's all. Because it'll lose contact if the centripetal force is equal to its weight, right? At the top, isn't it, at this point, there's a chance of it losing contact with the road? Come on, that's because if the weight acting down becomes equal to the centripetal force, then it's going to just lose contact.
Is it 34.3?
I think so, yeah, because 3 people said that. So those are the 2 forces acting. And when it loses contact, what is Fn? Somebody said it. Yeah, if it loses contact, there's no normal reaction, isn't it? See, there's only normal reaction if it's touching a surface. Are you with me on that? So if it's not touching, it's 0. So the net force in this case is actually Fn minus mg. I'm trying to give you a perfect thing. Actually, the net force is Fn minus mg, isn't it? And that should be set equal to mv squared by r. But since Fn is 0, I have not included that. Okay. And therefore, .3 meter per second. So we've got to be really careful when you design something like that, even if it's a bridge, or in this case it's a hilltop. You have to be careful. People can just be flying. Yeah, it is banked at an angle of 20 degrees. But this guy is driving at 24.5 meter per second, and reading the problem, it appears as if he has a chance of skidding, right? He has a chance of skidding if there's no friction. So what do you do first? Okay, I mean, do it your way, but draw the diagram. Read it carefully. Read it.
We gotta imagine the embankment and do the net force from the embankment. Right?
Okay, so then you're starting from the basics. You can do it that way. Start from the basics, get the equation, but you didn't have to start that far down if you just, you know the mass, you know the radius.
Fn cosine theta is equal to mass times gravity.
Yeah, that's true. F cos theta is equal to mass times gravity. Okay, work your way from there up. Because we can do it in many ways. Yes, Ken?
And you just said the force of friction equal to the acceleration, the centripetal acceleration?
Now, the statement that you just now said, you said force is equal to acceleration is wrong. Just now you said set force is equal to,
The force of friction.
a force can only be equal to another force. You know what I'm trying to say?
Oh, yeah, well, the force of centripetal acceleration.
Oh, so you're trying to say set the centripetal acceleration, centripetal force is equal to the force of friction.
Yes.
Won't work because there's already banking. Because banking also gives us a part of the centripetal force, doesn't it?
Doesn't that factor into the force of friction?
No, they are completely different.
Doesn't it?
Do it your way. If it's a flat road, there's only friction. If it's banked, there's both friction and Fn sine theta. Isn't that the component that provides the centripetal force, Fn sine theta? So there's both. So how do you do this?
So the force friction equals the centripetal force minus.
Yes, Fn sine theta is.
Okay, now you're thinking correctly. I'm looking at using the time properly. Okay, let's watch this. Centripetal force due to banking. I'm calculating that. Isn't that the formula for centripetal force? No, actually, that's the total centripetal force that is required. All right, before you write, did you understand that statement? To keep the car on the road, that's how much you actually need. Mass times the square of the velocity divided by the radius. That comes out to 3001 Newton. And banking provides Fn sine theta. And that is the weight, Fn, resolved into Fn sine theta and Fn cos theta. Okay, Fn cos theta is equal to mg. So from that I can find Fn because I have mg. Okay, I'm trying to say that's Fn cos theta. So mg by cos theta, that gives me Fn. After I get Fn, I can use that to find Fn sine theta. So I got that much. Now if I take the difference, I know how much the force of friction must be, isn't it? Okay. So I take the difference between them, and then I know coefficient of friction is nothing but force of friction divided by the normal force, and I get 0.13. This would be a 3.5 question. Now, what are the forces that act on this one? Yeah, Ft acting up and mg acting down. That's all right? Okay. Oh, now I understand that was about this one. Sorry. What are the forces that act on this? Fn and then mg down and Ft to the right. Everybody should be clear about that. Okay. There are only three forces that act on object 1. And does this question talk about friction also? Yes.
Yeah, we do.
Yeah, it does. So that's why there is the next force, the fourth one, friction, is always opposite to the motion. So yes, there is friction. Now coming to the second one, there are only two forces, mg and Ft. All right. So when you look at the forces along the x-axis, surely this is going to the right, isn't it? Therefore, you have to take this minus this. Should be equal to the mass times acceleration, the product. And then for the second one, m2g minus Ft, because it's going down. Isn't this going down? Therefore, this must be greater than this. That's why I'm putting this first. m2g minus Ft, m2a. Now add the two equations. You can solve it any way you like, but I just thought adding them will get rid of the positive Ft and the minus Ft when you add them. So you can substitute or do whatever you like, and then when you add them, this is what you get. On the right side, a is common, so I've taken m1 and m2 outside there. A is common, m1 plus m2, and then make a the subject. So it's m2g. And then I also added the fact that friction is mu times Fn, isn't it? And Fn is mg. Fn is mg. So I have mu times mg, okay, divided by m1 plus m2. Therefore, acceleration, now it's just plugging in the numbers that's given there. So the masses are given, mu is given, just plug it in there, you get the acceleration. So A is draw the free body diagrams, B is calculate the acceleration, and C is find the tension. Now to find the tension, you just have to plug it back into one of the equations. Yes, Lee?
How can you tell that the box is moving when it says the one on top is at rest?
Initially it's at rest.
But it's gotta be accelerated.
Yeah.
Because 2 is,
If you set it up like that, don't you think it'll move when you let go? Initially it's at, yeah. Because the friction is not enough. Yeah, it's not enough to keep it there. Is that clear? Because the hanging mass is 15 kilograms. And the other one is only 8. So it's a much heavier mass here, so it has to come down. Okay. So plug it back into that equation and then find Ft. would get the tension as 56. Oh, now the question comes up. All right, 56.25 newtons. Just wanted you to remember that. Oh, I have to say something.
I mean, you can do that by just dropping two different objects.
Yeah, but they wanted to check it on the plane anyway. Okay, this is how we get it, and everybody knows. A is mg sine theta divided by the mass, and that's how you get g sine theta. Okay, I just wanted to ask you this. That's what I'm trying to draw. What if there is friction? Can you find the acceleration? Yeah. All you got to do is? Yeah, minus friction divided by the mass, isn't it? That's it. Minus friction divided by the mass, if there is friction. Yeah. And you know that frictional force is mu Fn? I'm just trying to add on to that question. That's just if there is friction. And if you assume that mu is 0.1, then frictional force would have been that much. And therefore, the acceleration would have now been mg sine theta minus that force divided by the mass. Again, mass gets cancelled. And then you would get a smaller acceleration, which is 0.41 times g instead of 0.5 g. Makes sense, doesn't it? If there is friction, it's going to be a little bit slower. Brings us to 24. I think I'm putting the questions at the end now. Two objects push on each other. The first object, A, has a mass of 30 kilograms and it accelerates at 2 meters per second squared towards the east. The second one has a mass of 7, and if no other forces are acting on the object, what is the acceleration of the second object? So the formula that you're going to use here is force is equal to mass times acceleration, isn't it? For sure, that's the only formula, but you have to be careful. Because they're pushing against each other, now you'll have to label them as force applied by 1 on 2 and force applied by 2 on 1. You have to be careful. That's what I'm going to do now first. Those are the two objects, 30 and 7. It's going to the east, 2 meters per second. I mean, that's acceleration. And you're asked to find the acceleration of the other one. Isn't that what we're asked to do? What happened? Did I draw it to the west? Oh, that's why you're... Oh, yes, I did. I'm sorry. I drew it to the west. I was supposed to draw it that way. What a mistake.
Either way.
Anyway, yeah, I mean, but technically I'm wrong. See, and they were all making fun of me. That's okay.
You just moved the 7 to the other side.
Yeah, it should, anyway, now I can't. It's too late. So now the force, how do you read that? How do you read that? Force due to 2. Yeah, force on 1 due to 2. I've labeled this 1. This is 2. So force on 1 due to 2 is equal to mass of... It's the force on 1, isn't it? If it's the force on 1, it should be the mass of 1. Just be careful about that. Okay, again, last time. Force on 1 due to 2. So you're not concerned about the mass of 2 now. Because you're looking at the force on 1, you take the mass of 1, which is 30, times its acceleration, which is 60. Okay. Now do the same thing. Force on 2 due to 1 is equal to the mass of 2. Yeah, but you know that by Newton's third law, force on 2 by 1 is the reaction of the force of... Yeah, right? You got it? Although it's tough to say it, but you understood what it means. Equal and opposite, that's why there's a negative sign. Therefore, I'm going to say minus 60. All right, be careful. Force on 1 due to 2 was 60. Therefore, force on 2 due to 1 should be minus 60. Is everybody clear on that? Okay. And that should be equal to the mass of 2 times its acceleration. Mass of 2 is 7 times its acceleration. Problem done. Minus 60 by 7. So minus 8.57. If that negative shows, it's towards the west. Okay, so my diagram is wrong, but the answer is okay. You understood that, right? I should have just, yeah. Okay, so that brings us to the last one. At least for this, I have the question set up.
You take their positions.
Yeah,
on-
Their X and Y positions for each.
Yeah. correct. But if you can write, I don't know how I did it. Maybe I used the ij, I think so. If you use the ijk, it'll be easier instead of using the cos and the sine.
Oh, no, I didn't do that.
Okay, either way you get the answer. Either way you get the answer. But
the IJ choose a K.
yeah, here, these are the forces given, isn't it? All right. What I did is, I just called them 1, 2, 3 first, so there's no confusion. And I wrote F1 as this. Does that make sense?
Yeah.
Minus 3i, minus 2j. Do you see that? Yeah, so that's force 1. Minus 3i, minus 2j. And then the second one, F2 is, I think you should try, minus 2i plus 3j. Okay. And
It's
third.
algebra all over again.
yeah. And that is 4i plus 4j. Now all you got to do is net force. Oh, the net force must be 0. Oh, that's magic? It's not magic because it says it must not accelerate, right? Acceleration is 0. If the acceleration is 0, then the net force is 0. So I know the net force is so that, okay, should not be so that. Net F is 0 because A is 0. Yeah, that's what I meant. Add all those, you get minus I. Add the j's, you get plus 5. Now F4 should be I minus 5j. All right, take note of that. When you add it, what you get after you add is not the answer. It should be the opposite of that. Okay. Otherwise, you won't get a 0. How many understood that? Let me try that again. Okay, good. When you add these, you get this. But that's not the answer because you want to add the opposite of that so that along with the 3, when you add this, it becomes 0. Is that clear? Okay. That's what I tried. It's been a great day. Thank you, guys.